Solving the planning problem in polynomial space. Now we consider how to solve the basic planning problem in polynomial space. The issues here will look quite different, and it will turn out to be a much more difficult task. The problem: recall that we have a set of conditions C equals to the collections of C1, C2, C3 until Cn, and a set of operators, the set O1, O2, O3 until OK. Each operator OI has a prerequisite list PI, an add list AI, and a delete list DI. Note that OI can still be applied even if conditions other than those in PI are present, and it does not affect the conditions that are not in AI or DI. We define a configuration to be a subset C prime, which is a subset equals to C, the collections of fancy C, which is the set of C1, C2, C3 until Cn. The state of the planning problems at any given time can be identified with a unique configuration C prime, consisting precisely of the conditions that hold at that time. For an initial configuration C0 and a goal configuration C star, we wish to determine whether there is a sequence of operators that will take us from C0 to C star. We can view our planning instance in terms of a giant implicit defined directed graph G. There is a node of G for each of the 2 to the n possible configurations, i.e. each possible subset of C, and there is an edge of G from configuration C prime to configuration C prime prime if in one step one of the operators can convert C prime to C prime prime. In terms of this graph, the planning problem has a very natural formulation. Is there a path in G from C0 to C star, where the 0 and the C star are fancy C? Such a path corresponds precisely to a sequence of operators leading from C0 to C star. It's possible for a planning instance to have a short solution, as in examples of the 15 puzzle, but this need not hold in general. That is, there need not always be a short path in G from C0 to C star. This should not be so surprising, since G has an exponential number of nodes, but we must be careful in applying this intuition, since G has a special structure. It is defined very compactly in terms of the n conditions and k operators. 9.6. There are instances of the planning problem with n conditions and k operators for which there exists a solution, but the shortest solution has length 2 to the n minus 1. Proof. We give a simple example of such an instance. It essentially encodes the task of incrementing an n-bit counter from the all zeros state to the all ones state. We have conditions C1, C2, C3 until Cn. We have operators O1 for I equals to 1 to 3 until n. O1 has no prerequisite or delete list. It simply adds C1. For I greater than 1, the index I, OI requires Cj for all j which is less than I as prerequisites, where j and I are indices. When invoked, it adds Ci and deletes Cj for all j less than I. Now we ask, is there a sequence of operators that will take us from C0 equals to the empty set to C star, the fancy C star, which is equals to the collections of C1, C2, C3 until Cn, the conditions of n conditions, the collections of n conditions. We claim the following by induction on I. From any configuration that does not contain Cj for any j which is less than or equals to I, there exists a sequence of operators that reaches a configuration containing Cj for all j which is less than or equals to I. But any such sequence has at least 2 to the I minus 1 steps. This is clearly true for I equals to 1. For larger I, here's one solution. By induction achieve conditions. The set Ci minus 1, Ci minus 2, Ci minus 3, and so on until C1 using operators O1, O2, O3 until using operators. Now invoke operator O3, adding Ca but deleting everything else. Again, by induction, achieve conditions. The set Ci minus 1, Ci minus 2, Ci minus 3, and so on until C1 using operators O1, O2, O3 until O(-1). Note that condition Ci is preserved throughout this process. Now we take care of the other part of the induction step, that any such sequence requires at least 2 to the I-1 steps. So consider the first moment when Ci is added. At this step, Ci-1, Ci-2, and so on till C1 must have been present, and by induction, this must have taken at least 2 to the I-1, then -1 steps. Ci can only be added by Oi, which deletes all Cj for all j less than I. Now we have to achieve conditions that set Ci-1, Ci-2, and so on until C1. Again, this will take another 2 to the I-1, then -1 steps by induction for a total of at least 2 times 2 to the I-1, then -1. After we time such a formula by 2, then we plus 1, which is equals to 2 to the I, then -1 steps. The overall bound now follows by applying this claim with I equals to n. Of course, if every yes instance of planning had a polynomial length solution, then planning would be in NP. We could just exhibit the solution. But 9.6 shows that the shortest solution is not necessarily a good certificate for a planning instance, since it can have a length that is exponential in the input size. However, 9.6 describes essentially the worst case, for we have the following matching upper bound. The graph G has 2 to the n nodes, and if there is a path from C0 to C star, then the shortest such path does not visit any node more than once. As a result, the shortest path can take at most 2 to the n, then -1 steps after leaving C0. 9.7. If a planning instance with n conditions has a solution, then it has one using at most 2 to the n-1 steps. Designing the algorithm, we've seen that the shortest solution to the planning problem may have length exponential in n, which is bad news. After all, this means that in polynomial space, we can't even store an explicit representation of the solution. But this fact doesn't necessarily close out our hopes of solving an arbitrary instances of planning using only polynomial space. It's possible that there could be an algorithm that decides the answers to an instance of planning without ever being able to survey the entire solution at once. In fact, we now show that this is the case. We designed an algorithm to solve planning in polynomial space. Some exponential approaches. To get some intuition about this problem, we first consider the following brute force algorithm to solve the planning instance. We build the graph G and use any graph connectivity algorithm, depth first search or breadth first search, to decide whether there is a path from C0 to C star. Of course, this algorithm is too brute force for our purposes. It takes exponential space just to construct the graph G. We could try an approach in which we never actually build G and just simulate the behavior of depth first search or breadth first search on it, but this is likewise not feasible. Depth first search crucially requires us to maintain a list of all the nodes in the current path we are exploring, and this can grow to exponential size. Breadth first requires a list of all nodes in the current frontier of the search, and this too can grow to exponential size. We seem stuck. Our problem is transparently equivalent to finding a path in G, and all the standard pathfinding algorithms we know are too lavish in their use of space. Could there really be a fundamentally different pathfinding algorithm out there? A more space-efficient way to construct the paths? In fact, there is a fundamentally different kind of a pathfinding algorithm, and it has just the properties we need. The basic idea proposed by Savage in 1970 is a clever use of the divide and conquer principle. It subsequently inspired the trick for reducing the space requirements in the sequence alignment problem. So the overall approach may remind you of what we discussed there in section 6.7. Our plan, as before, is to find a clever way to reuse space, admittedly at the expense of increasing the time spent. Neither depth-first search nor breadth-first search is nearly aggressive enough in its reuse of space. Both need to maintain a large history at all times. We need a way to solve half the problem throw away almost all the intermediate work, and then solve the other half of the problem. The key is a procedure that we will call path of C1, C2, L. It determines whether there is a sequence of operators consisting of at most L steps that leads from configuration C1 to configuration C2. So our initial problem is to determine the result yes or no of path C0, C star, and to the end. Breadth first search can be viewed as a following dynamic programming implementation of this procedure. To determine path of C1, C2, L, we first determine all C prime for which path of C1, C prime, L minus 1 holds. We then see for each such C prime whether any operator leads directly from C prime to C2. This indicates some of the wastefulness in terms of space that breadth first search entails. We are generating a huge number of intermediate configurations just to reduce the parameter L by 1. More effective would be to try determining whether there is any configuration C' that could serve as the midpoint of a path from C1 to C2. We could first generate all possible midpoints C'. For each C', we then check recursively whether we can get from C1 to C' in at most L over 2 steps, and also whether we can get from C' to C2 in at most L over 2 steps. This involves 2 recursive calls, but we care only about the yes-no outcome of each. Other than this, we can reuse space from one to the next. Does this really reduce the space usage to a polynomial amount? We first write down the procedure carefully and then analyze it. We will think of L as a power of 2, which it is for our purposes. Path of C1, C2, L, where the C1, C2, and L are input parameters. If L is equals to 1, then if there is an operator O converting C1 to C2, then return yes. Else return no. And if L is not equals to 1, that is L is greater than 1, then what should we do? We enumerate all configurations C' using an n-bit counter. For each C', do the following. We compute x equals to a recursive call of path of C1, C', and the ceiling functions of L over 2. We delete all intermediate work, saving only the return value x. Then we compute y equals to the output of path of C', C2, and the ceiling functions of L over 2. We delete all intermediate work, saving only the return value y. If both x and y, the return value by the recursive calls, are equal to yes, then return yes. Okay, now we break out from the for loop. Now if a yes was not returned for any C', then return no. So this is very logical. Again, note that this procedure solves a generalization of our original question, which simply asks for path C0, C star 2 to the n. This does mean, however, that we should remember to view L as an exponentially large parameter, log of L equals to n. Analyzing the algorithm, the following claim therefore implies that planning can be solved in polynomial space. 9.8. Path of C1, C2, L returns yes if and only if there is a sequence of operators of length at most L leading from C1 to C2. Its space usage is polynomial in n, k, and log L. Proof. The correctness follows by induction on L. It clearly holds when L equals to 1, since all operators are considered explicitly. Now consider a larger value of L. If there is a sequence of operators from C1 to C2 of length L', which is less than or equals to L, then there is a configuration C' that occurs at a position the ceiling functions of L' over 2 in this sequence. By induction, path of C1, C', and the ceiling functions of L over 2, and a path of C', C2, and the ceiling functions of L over 2 will both return yes, and still path of C1, C2, and L will return yes. Conversely, if there is a configuration C', so that the path of C1, C', and the ceiling functions of L over 2, and a path of C', C2, and the Stealing functions of L over 2 both return yes. Then the induction hypothesis implies that there exist corresponding sequences of operators. Concatenating these two sequences, we obtain a sequence of operators from C1 to C2 of length at most L. Now we consider the space requirements. Aside from the space spanned inside recursive calls, each invocation of path involves an amount of space polynomial in ANK and log L. But at any given point in time, only a single recursive call is active, and the intermediate work from all other recursive calls has been deleted. Thus, for a polynomial function p, the space requirement S of nkl satisfies the recurrence. That is, S of nkl is less than or equals to p of nk log L plus S of nk, the Stealing functions of L over 2, and S of nk1, which is less than or equals to p of nk1. Unwinding the recurrence for big O of log L levels, we obtain the bound S of nkl equals to big O of log L times p of nk log L, which is a polynomial in nk and log L. If dynamic programming has an opposite, this is it. Back when we were solving problems by dynamic programming, the fundamental principle was to save all the intermediate work so you don't have to recompute it. Now that conserving space is our goal, we have just the opposite priorities. Throw away all the intermediate work since it's just taking up space and it can always be recomputed. As we saw when we designed the space-efficient sequence alignment algorithm, the best strategy often lies somewhere in between. Motivated by these two approaches, throw away some of the intermediate work, but not so much that you blew up the running time.